start. Okay, let's start. So, in our last lecture, we have learned about the basics of fuzzing and the key mechanisms of gray box fuzzing. And today, we are going to learn one of the most influential or impactful gray box fuzzers nowadays, and it is called American Fuzzy Loop. So this is today's outline. So first we will go through an overview of this AFL project, and then we will learn different key mechanisms of AFL. The first one is instrumentation, the second one is seed handling, and the third one is about seed mutation, and the last one is parallel fuzzing. So first, let's have a look at the background of AFL. So AFL is a gray box fuzzer developed by this guy. I believe his name should be pronounced as Mikhail, and I can't pronounce his surname. And when this guy was working for Google, so basically this fuzzer was owned by Google. And it was named after a rabbit, if you wonder what is the name. So it is a rabbit rather than, do you know this symbol? Australian Football League. So AFL actually refers to a rabbit. And it is currently considered a standard for gray box fuzzing. And because it has contributed significantly to the research of gray box fuzzing. And many research or academic fuzzers are actually forks of AFL. And let's have a closer look at the author of this great fuzzing tool. And this guy, Mikhail, whatever, is actually a very famous white hat hacker. And if we look at his surname, he's some kind of ski. So he's actually from East Europe. He's a Polish guy. And maybe they like to ski, so the weather is cold, so they have the name of ski. But no offense to those people. And this is him years ago. Today here is actually years ago. And he's actually one of the most influential white hat hackers. And this was him. And this is him now. And this is also him. Sometimes people could look differently in different photos. And I believe this one is closer to reality. And I have never met him in person, but I think he's a very great person. And we will learn about it through his code. So, as I just said, the code repository is maintained by Google now because it was created when this guy was working for Google. And if you click on this link, if you get to the web page, you may notice that in this year, Google has archived this repository. So it is now read-only, so we cannot make contributions to this repo. And the reason is because it's not because AFL is so-called outdated. It's because now we have another project called AFL++, just like C and C++. So AFL++ was actually maintained by a group of people around the world. And it is actually more like, because as I just mentioned, there are many academic fuzzers based on AFL, and many of them could be integrated together into one fuzzer. And this AFL++ is more like an integration of those academic fuzzers based on AFL. And so we can consider AFL is getting replaced by AFL++. But we still learn AFL here because many of the key concepts are still the same. And the code of AFL is very elegant. And talking about code, let's have a look at the code repository of AFL. And here are all the folders, and here are all the key files. So for folders, you don't have to, this page has a lot of information, you don't have to remember all of them, so this is just for those who are watching the slides, this to provide information. So this is, so for the first directory, we can see that it's called dictionary. Actually, it is some example dictionaries provided by the author of AFL for dictionary-based mutations. And there are some experimental features, which were, many of them were converted into academic papers. And this lab dislocator is similar to address sanitizer. It is to increase the sensitivity of the fuzzer. And this lab token cap is to automatically generate dictionaries with the project. And LLVM mod is the LLVM-based instrumentation. So it's one of the way to instrument code into the target program. And it also supports Qumil-based instrumentation, which is to instrument binary programs. And the author of AFL also provides a set of initial seed inputs for the users. And here are the list of files, the list of code. So the first one, it is actually a mixture of the fuzzer itself and a set of utility tools. So the first one is a utility tool that could be used to analyze the format, the input format of the target program. And the second one here is AFL's assembler for instrumentation again. We will learn about this later. And this is a key file, the main logic of the fuzzer. It's a single file that contains over 8,000 lines of code. And I don't suggest you to try this at home, so it's better to keep your source code files smaller than this. But since this guy is not only a great hacker, he's a great developer. He can write a code with 8,000 lines without a single bug. So this is, don't try this at home. And AFL GCC is a wrapper for compilers to do instrumentations. And AFL show map is an utility tool to show the bitmap content, and we will learn about the keyword bitmap later. And the last tool here is called AFL cmin, which is to minimize, because users need to provide the initial corpus of seed inputs. And this utility could minimize the initial seed inputs according to the coverage of them. So these are roughly everything about AFL, but there are some more details. As you can see, we haven't covered all the files there, but these are the main tools and utilities from this repository. And the overall workflow of AFL is rather simple, so because it's highly automated. So the first step is to instrument the target. Remember in our last lecture we talked about instrumentations. So instrumentations basically means that we want to inject some code into the target program. And AFL can deal with source code or without source code. So even without source code, we can somehow inject logic into the target program, or even if we don't inject logic into the target program, we can still collect runtime coverage information with some hardware features. And we will talk about the details of how do we do instrumentation later today. And there are some other preparation steps. So the first one is we need to prepare the initial seed inputs. And if we provide a lot of inputs, like thousands of initial seed inputs, what we can do is we can try to use one of the utilities to minimize the seed coppers, but that is optional. And we can, for some input with structures, we can also use dictionaries, prepare some dictionaries to do the mutation better. And we should also study the command line options of the target to see what are the potential attack surfaces of our target. And the last one is, if we run AFL for the first time, we should set the CPU performance mode of the machine we are using. But this is we will talk about this in the practice today. So after we have done the instrumentation and preparation, what we can do is we can just run AFL fuzz to actually start the fuzzing process, and we can observe for key information from the UI it provided to check if we have run it properly or not. So what's your question? Corpus is like a collection of seed. It's a set of seeds. It's like a seed pool or seed queue, so things like that. So, and if we find crashes, if we could find crashes, what we need to do is first we need to do crash triaging, which means that later I'll show you with an example when we do the practice. So many of the crashes are actually linked with the same bug. So one bug could cause multiple crashes. And that's why we need to do some kind of root cause analysis and try to debug the target. Because if we want to report bugs to the developers, we need to write a bug report. We need to do some simple debugging to explain the root cause of the bug. And this is the overall workflow of using AFL. And just now I talked about we can observe key information from the user interface of AFL. And this is a user interface of AFL. As you can see here, is a command line user interface. So let's have a quick look at what are the key components here. So from the banner of this user interface, we can see that there's a name of this process, this fuzzing process, this instance. And we can run multiple instances of AFL in parallel to maximize the usage of CPUs of that machine. So nowadays, in many machines, even in our laptops, we have multiple core CPUs. So we can make use all of the CPUs to do fuzzing. And in this part of the UI, it reports the cycle information. So it actually means that AFL is cycling through, because gray box fuzzing, they need to maintain a queue of seed inputs. And it actually cycles through the queue of seeds. And in this stage progress part, it actually shows us the current mutation operator being used by AFL. And the total executions actually means the total number of test cases we have tested with AFL. As you can see here, we have started this, in this screenshot, the fuzzing instance has been started for 12 minutes, and it has already tried 900,000 of test cases. So AFL is actually a very, very powerful tool. It's a very, very powerful tool. It can automatically generate a large amount of test inputs. And here are the report for different mutation operators, so we can see the performance of different mutation operators we use. And the term path here used by AFL is actually different from what we have learned in control flow graph. The path, execution path is different. One path here is actually corresponding to one seed input. We will learn about more details later, but don't worry about that. And crash here is defined as triggering abnormal signals. So in Linux systems, we have signals, the signaling system. And for example, if the program runs into a segmentation fault, we will get a signal. We will get a signal of 11. So this is so the signal actually represents whether the program runs into some problem or not. And for example, if we run into a board like a certain field, the signal value will be 6. If we run into a floating point error, which is often related to divide by 0, that is, the signal is 8. So we can use different signals to check whether we run into crashes or not. And you may also notice that there is a line called unique counts. So unique counts are actually timeouts. So AFL actually measures the average execution speed of different test inputs. If a test input uses a long time to execute, it might be treated as a timeout. And that timeout is often useful for us to detect performance issues of the target, or sometimes infinite loops. So this is also useful. And for map coverage, and this coverage here is actually related to a specific type of code coverage used by AFL. And we will learn more details about the coverage in AFL later. And another important information here is stability. So one seed input could have different coverage. So one test input sometimes could have different coverage in multiple runs. That is because some programs are random by nature. So one of the randomness comes from the direct use of random values. So maybe the program executes use some random inputs, or use some random numbers to determine its execution. Sometimes it happens. And another major source of randomness during execution is from multi-thread programs. So if the program runs with multiple threads, the execution order of different basic blocks in different threads could be different. So stability actually refers to the randomness during execution. So if the execution trace or the code coverage differs very much across different executions, then the stability is lower. So this is how stability works here. And this UI, as you can see, it's very informative, and it provides us a lot of information. And it looks also quite nice, and it's actually implemented purely by printf. No library is used. So AFL doesn't, the original AFL, not AFL++, actually doesn't have too much dependencies. The author has written a lot of utility code for this fuzzer. And by looking at the source code of AFL, I found this. So can you see this? So this comment, before he started to write the code to print out this UI. So the author said, Lord, forgive me this. So actually you can see here, this is precise timing starting from here. So it's printed out line by line by using printf. So this author is a very good coder. And that's all about the background and overview of AFL. Let's have a look at the key mechanisms or key components. The first key component we care about is instrumentation. So there are actually two types of instrumented code. So remember, let's first think about because we want to inject code into the target for two reasons. The two reasons are, first, we need to somehow allow the father to control the creation of new processes of the target program. And that's the first purpose. And the second purpose is that we need to collect coverage information. We need to collect coverage information during execution. So the first feature is related to the type of instrumented code called fork server. And the second one is related to some coverage collection instrumentation. And because remember, we need to control the process, we need to collect information, and this actually requires communications between the target program and the AFL. So how do we do inter-process communication here? So have you ever done any coding related to inter-process communication before? No? Okay, so there are many ways of doing inter-process communication. So because we know that for operating systems, different programs run. If we start running a particular program or application, the operating system actually helps us to create a process for that application or program. And if we want multiple programs to communicate, so if we want to do this communication between different processes, we need some intermediate channels for this communication. And one of them could be files. So maybe one process could write to a file, and the other process could read from that file. And that's the simplest idea. And we could also use databases. So maybe one process writes into the database, and the other process read from the database. But those two approaches are very slow because we have to deal with the file system. We have to even run the database. So that's slow. We have some faster approaches provided in Linux. So for fork server, we use pipe. We use the mechanism of pipe to do this inter-process communication. For coverage collection, we use the concept called shared memory to do inter-process communication. And we will learn about the details in the next few slides. So for instrumentation, if we have source code, we can use these few tools. These are the compilers. If you compile the AFL project, you can get these few compilers. And GCC and CLang are for compiling C code. G++ and CLang++ are actually used for compiling C++ tools. And if we use them, actually AFL will instrument the target program with hard-coded assembly code using the utility called AFL-AS. And this approach actually is because the assembly code or the instrumented code is hard-coded in assembly code. So this actually is dependent on the CPU type, and it only supports Intel x86 or x86-64 structures. So these are not just for Intel CPUs. So if you use AMD CPU, you can also do this. And this is only for the Intel instruction set. It's more like a standard for CPU instructions. So this is the source code written by the author, the hard-coded assembly. So basically, this is very hacky. And we have another approach to instrument source code, and this is related to LLVM, the project LLVM. And the tools we will be using to do this is called AFL CLangFast and AFL CLangFast++ for C++. And this instrumentation is done on the LLVM intermediate representation level. So have you taken the compiler course before? Yes? Okay, good. So you must know intermediate representations, right? So it is actually done on intermediate representations level. So the advantage of this is that it actually enjoys, because this injected code will become part of the program. And if we instrument it in IR level, the injected code will enjoy the compiler optimization. So it will be optimized by the compiler together with the original code of the program. So this executes faster actually, normally. So it is called CLangFast. And because LLVM is a well-structured project, a framework, so it's easier for us to implement more complex instrumentation logic. So here, because if we just want to use the first approach to do this implementation, we have to manually write those assembly code, and which is not very flexible unless you are very good at writing assemblies. And this is, of course, this is across platform because it's instrumented in IR. We can compile it for different CPUs. So this is another advantage. However, it also requires us to install LLVM, and somehow this AFL code, because it's now archived, it's no longer updating, so the version of LLVM required is a little bit old. And normally we prefer to use this approach to do the instrumentation unless we cannot install LLVM properly on that in that environment. So this is how we do instrumentation with source code. And without source code, we can use AFL QEMU. So have you heard about QEMU before? Actually, QEMU stands for Quick Emulator. So it actually is like a virtual machine. It's like a virtual machine, like VirtualBox or VMware, but it's open source and very lightweight. And what we can do is it also provides some kind of intermediate representations. And AFL actually can also instrument code into QEMU IR. And QEMU can run in user mode or full system emulation. In user mode, the system calls are delegated to the host operating system. So user mode emulation is normally relatively faster than doing full system emulation. However, using this emulator, as you could imagine, is much slower than we run the target program on the native host system. So this could be very slow. And it is provided by AFL in its repository. You could see there are some links on these slides. You can click on them to get more information. So So this QEMU mode actually can help us to do instrumentation without source code. That's its advantage. And we can also use some binary rewriters. And if you click on this link, you can get a list of binary rewriters. So which means that we can use those tools to rewrite the already compiled binaries to inject logic into them. And it is normally faster than using AFL QEMU. However, it is sometimes not very stable because of the limitations of those binary writers. So you may not be able to instrument certain targets. You may not, sometimes even if you can instrument them, you may encounter some weird bugs. So we don't recommend this as well. And there are some new features to do this instrumentation without source code, or it's actually not instrumentation. It's like only collecting runtime information or execution coverage information with the support of some hardware features. So because it is actually not really instrumentation, we cannot, CPUs cannot modify code. So they can only execute instructions and collect information during the execution. So we cannot inject fork server because fork server is not related to information coverage, information collection. But we can still collect the coverage with some hardware features. For Intel CPUs, we can use Intel processor trace feature. If the CPU supports. And for ARM CPUs, we can use core site. So these are the trend. And this comparing to QEMU and binary writers, using CPU support is normally much faster and much more stable. So, but overall, if we have source code, that's the best case, and we don't, because this is too hacky, and we don't learn about them in details in this course. Let's learn how do we do the instrumentation and how the instrumentations work with source code. So the first background, so the first type of instrumentation we are going to learn is fork server. And the key of fork server is a system call called fork. So in Unix or Linux system, the system called fork creates a new process by duplicating the calling process. Actually, if you are running a Linux system, every process you are interacting with is actually forked from the very first process of the operating system. So fork is actually used for creating new processes in Linux. And the new process created is called the child. And the calling process of this fork function is called the parent process. And it has a unique feature called copy on write. So the child of the child process will only create a new copy of some specific memory regions, and for the heap of the child, it is actually reusing the parent's heap, unless the child is trying to write into the heap. It will make a copy. So in this case, so this is an example here. So this is the main process, and the fork will return an integer. And if this integer is smaller than 0, then it means the fork has failed. It runs into some error. And if the value is 0, then it means that because fork means we are creating two processes. We are creating a new copy of this parent process, and this parent process still exists. So we are actually like really having a fork in the process, and so we will have two processes after calling fork. If they count the original process in. But how do we tell which process are we in, right? So after calling fork, so we use the return value here. So if the return value, if what we see in the process after calling fork, if we see the return value is 0, then it means that we are in the child process. Because the child process by default doesn't see its own PID, but of course it can get its own PID. And the parent process, if the child PID is larger than 0, then the parent process can get the PID of the child process it has created using the return value here. So this is fork. And the advantage of fork is that because it has the mechanism of copy on write, it is very fast, and it actually saves the actual memory we use, because we don't create a duplication of the memory when we create new processes. And there are more information on the Linux manual page, so you can check it if you are interested. And the other important thing we need to learn before we learn the details, the mechanism of fork server, is pipe. So just now we mentioned that pipe is used as a mechanism for inter-process communication. And pipes and FIFOs, or first in, first out, or named pipes, provides a unidirectional inter-process communication channel. So each pipe has a read end and a write end, and data written to the right end of a pipe could be read by the other process from the reading end of the pipe. So it's literally like a pipe between some tunnels between different processes. You can imagine it as a file there. It actually many of the structures we encounter today are described as files in Linux, in POSIX operating systems. So AFL actually uses two pipes for communicating with the target program. One of them is to be written by AFL and to be read by the target program. The other one is to be written by the target and to be read by AFL. So you can imagine AFL creates two files. With one file, AFL writes content but doesn't read. With the other one, AFL listens to the changes of that file. And the target program will do similar things with those two files. So this is pipe. And you can get more information from the official Linux manual page. And the source code of fork server is the instrumented code is here. And in AFL, in the fuzzer side, it has two parts related to fork server. The first part is initializing fork server, and the second part is for every time we execute, the fuzzer tries to execute a test input, it needs to interact with the fork server. And the initialization of fork server will only do the health check, because setting up fork server is sometimes we could run into errors when we try to set up fork server. So we need to do some kind of initial health check of whether this fork server has been set up correctly or not. And And we are not very interested in this. We are more interested in how does fork server work for every when the father tries to execute a test input. And we will learn it here. So remember, AFL uses two pipes for communicating with the fork server, with the target program. The pink one is for AFL to send a message to the target program. And the blue one is used by the target program to send messages to AFL. So let's remember this. And let's start with AFL's main process. So every time when we start fuzzing, when we just start fuzzing, there's only one process, and that is AFL's main process. And then AFL will do a fork here. And it will keep its original process here. And fork in Linux is often followed by exec or some variations of exec. So it actually invokes, this one actually is like popen in Python. It invokes a new program as a new process. So when we do this fork, what happens is the parent process will keep running as AFL's father process, and the child will execute execve, which means that it will inherit, it will be able to specify some environment variables in this execution. So it will use this to execute the target program. And this one, because we have executed exec here, so this child process will become the process belonging to the target program. And because we injected the fork server at the main, normally we inject it at the main function of the target program. So because every program starts with the main function, so it will, the fork server's logic is basically a loop. So it will stuck in this loop here. And let's have a closer look at what happens here. So first, it will wait from input from AFL. It will wait from the pipe of the pink one, because the pink one is used for AFL to send messages. So it will wait here, and AFL's process will write to pipe, and then wait for the feedback from the target. And it writes to pipe, it just writes a random integer into the pipe. Right? I forgot what is the integer there, but it just writes an integer to the pipe. So once the target process received the message from AFL is actually telling that, okay, let's try to test a new target. Let's try to test a new input. So this message is like telling the target process, get ready to receive a new test input. And then this test process, later you will know why it is called fork server here. So this target process will fork a new process here. And this process, it forks here. So the child, the parent process, will continue running as the fork server logic here. And the target process will exit the fork server loop, the fork server logic, and resume its normal execution as how it should work. So because we are instrumenting the target process, these are some extra logic for the target program. So if we exit the extra logic here, we will run into the normal routine of the target process. So it will it will have, if the child process will be used for running the test input here. It will be used to execute the test input. And then, because remember in fork, the parent knows the value, the PID of the child. And then the target fork, the fork server will tell AFL the PID of the executor process. We tell the PID of this green child process here to AFL, and it will wait for the executor to finish. And AFL will receive the child PID here, because it needs the PID to monitor the health of this process. Because in real world, in real scenarios, it could be very complicated. This process could could be ended with any reasons, maybe out of memory, maybe it's out of power if you are using a laptop. So there are many different reasons, and AFL needs to monitor the health of both the fork server and the target process, and it will need the PID of the child. So it is actually received from the fork server. And after receiving this PID, it will wait for pipe input again. So now you see both of them are waiting here. AFL, the father, waits for the input from the fork server. And this fork server waits for the input from the actual executor of the test input. And both of them are waiting, actually. They are essentially waiting for the execution to finish, execution of the test input to finish. And once the execution of a test input finishes, the fork server can get the exit signal of the child process here, and it will send it to AFL, and this is what AFL is waiting for. It's waiting for the signal. So it will tell AFL the signal of the executor and wait for pipe input again. So it will tell AFL about the signal here. And AFL will use the signal to check if there is a crash with the test input or not. And then it will use the signal to handle the execution result. It will generate next test input. And then once the next text input is ready, it will start another iteration of the loop. So it will tell the fork server, okay, it's ready for receiving next test input. And let's run this. So this is one whole round of communication between AFL and the target program. So remember in our last lecture, we mentioned that the execution speed of the target could be speed up by the father, right, by doing some instrumentation. And this smart design is actually how the father could speed up the creation of new testing process, new target program process. This is because whenever we create a new process in the operating system, we need to do a lot of environment setup. We need to set up the stack, set up everything for the new process. And because we are injecting the fork server, because this fork server actually, it is actually like a server waiting for the requests from the father to tell it to create new child processes. So this creating the child process here is actually much faster than creating a totally new process, because we have skipped those environment setup for running new processes. So this is why we can speed up somehow speed up the execution of the target program with instrumentations. It's basically like we are injecting some. We are not starting from the execution of every child process from the very start. We are actually skipping some setup done before. So this is why it is faster. It is faster, and there are some even more faster ways of executing the target with persistent loop. But we won't learn that here because it has some drawbacks, and this design of Fox server is relatively stable. And that's about how Fox server works and how it helps to speed up the execution of the target program. And now let's learn more about how do we use the instrumentations to collect coverage. So before we learn it, we need to learn how the coverage information is passed from the target to the fuzzer. So the mechanism of sharing this information is called shared memory. And in POSIX, shared memory APIs allows process to communicate information by sharing a region of memory. So this is more straightforward. So those two processes, they could access the same region of memory. And in AFL, this piece of shared memory, the default size is 65,536 bytes by default. And it actually is used to store the coverage information. You can view it as an array of bytes or unsigned chars. So the mechanism of this is that the target program will write to the shared memory, and AFL will read from the shared memory. And the shared memory is known as bitmap in AFL. So this shared memory is often referred to as so-called bitmap in AFL. And you may wonder, it is actually full of bytes, right? Why it is called a bitmap? Because AFL, the design of AFL actually makes use of array bit here. And we will learn about it in our next slide. And you can get more information about how shared memory works in the manual page of Linux. And this is how the target writes to the shared memory. So the first thing we need to care about is what is instrumented to the target program to collect the coverage. And this is the source code of doing this instrumentation in LVM IR. So basically what we can get from this source code is that for every basic block of the CFG, you can consider the basic blocks are from the control flow graph. So for every basic block, we assign an integer ID to that basic block. And then we do some calculation and write something to the shared memory. So what is written to the shared memory here? So in order to write to a piece of array, to an array or to a piece of memory, we need to first locate the index we should write to, right? So the index here is calculated as the ID of the previous basic block, right shift by 1 bit, XOR the ID of the current basic block. And this is used as the index here for accessing the bitmap, the shared memory. And then we plus 1 for that bitmap value here, for the value in the shared memory plus 1. So this XOR, as you can see, is actually calculated from the ID of both the previous basic block and the current basic block. So it is actually like a transition between basic block. So this ID is actually not given to a particular basic block. This index here is actually given to transitions of basic blocks. And it is actually not real so-called path coverage. They are just basic block transitions. And because we do this +1 here in bitmap with the ID, so you can see each index, actually each byte of the bitmap represents a unique basic block transition. And the value here means how many times we have executed that basic block transition in this one run, because we could have loops. We could execute a basic block transition multiple times during one execution. So each of the value here is actually the number of times that basic block transition has been executed. And let's do a level here. So AFL actually uses the value of the ID of previous basic block right shift by 1 XOR the ID of the current basic block as the unique ID of the basic block transitions. So why do we need to do this right shift by 1 here? So why do we need to do this? We only have two options for this. Okay, it's quite even. The actual reason is that the correct answer is the second one. So because the correct answer is the second one, because the calculator we use is XOR. XOR, if a value XOR itself, what do we get? Let's say 1 XOR 1, 0 XOR 0, what do we get? A value XOR itself. 0, yes. We always get 0. So there are some cases where a basic block would loop back to itself. So in that case, if we don't shift by 1, we will always get 0 in that case. And there could be multiple basic blocks in one program that would loop back to itself. So if we don't shift by 1, we cannot differentiate between those cases. So that's why we need to do this right shift by 1. So there are many detailed considerations in the source code of AFL. There are many details. Okay, that's all about instrumentation. Let's have a 3 minutes break. Sorry, I can't give you more breaking time today because we have a lot of content to cover. And okay, let's resume at 3:05. Okay, let's continue. So just now we covered how the two types of instrumentations used by AFL and how do they work. And now let's learn how does AFL handle seed. So the first one is how does AFL store new seeds? And the conclusion, in summary, AFL stores a test input because we have learned gray box fuzzers need to store new inputs. So the conclusion is that AFL stores a new seed if it can cover more than one new branches or new basic block transitions. And this is how we reach to the conclusion here. So in our last lecture, we have learned about the key mechanisms of gray box fuzzing. And this is actually a screenshot from the last lecture. So what we add to the, because in the third example, in the third question, the fuzzer can actually deal with this very complex nested if. It's because it is aware of branch coverage, and it will keep test input that can cover a new branch as the seed here. So branches are actually similar to the basic block transitions used by AFL. So that's why AFL can do this. And or it will actually keeps this will definitely, if a new test input can cover more than one new branch, it will definitely be kept. Or because remember in bitmap we store the number of times executed for a particular basic block transition. So if this new input can increase the loop count of a branch to a specific value, then it will also be kept here. But you may actually calculating this is very tricky. And how do we do it very compactly, and how do we do it very effectively? So actually AFL has a very smart design to store the loop count. And but we won't explain in detail here. That's too much of details. And let's continue. So basically you just need to know that whenever a test input can cover a new branch, AFL will keep it as a seed. So let's come back to the UI here. And here are some information related to storing of seeds. Remember, the total number of paths here is actually the total number of seeds maintained by AFL. And you may see two values here, two percentage here. So the first one is the number of branch covered by the current seed divided by the bitmap size, which is by default this value. So this is like the coverage, the coverage of the current seed. And you can make a guess of the second one. The second one is actually the coverage of all the seeds. So the right-hand side value is always larger than or equal to the left-hand one. And you can also see this value here. So this is actually the average loop count for the branches. So because AFL is actually making use of every bit here, so that's why it is called a bitmap. And if you are interested, you can click on the link of the previous page slides to check the source code of AFL and see why it works. Let's continue. So in our last lecture, we mentioned that there are two strategies that could be taken by gray box fuzzers during fuzzing, and one of them is related to the decision of which seed should we use next for fuzzing, for creating new test inputs. Which seed should we use next? And for AFL, it actually maintains something like a priority queue, and some seeds are marked as favored. So for priority queues, maybe this is the first time you encounter this term, but in real life, maybe you have always seen this on those public transportations. So they are priority seats. So these are like, so some people will get the priority for taking that seat, right? And for AFL, it's like some seats have the priority to be used to generate new test cases. And how does it work? How does this priority queue work here? So in one cycle, the AFL will go through the queue of the seeds one by one. It will check the queue of seeds one by one. And if that seed is not marked as favored, and if that seed is not marked as favored, and there are still favored seeds which are not visited yet, AFL will skip that seed in this cycle. And then AFL will go to the next cycle if all the seed in the current queue has been visited. And whenever a new seed is discovered, it is appended to the end of the queue. So this is roughly how this priority queue works. And you may wonder, how are the seeds getting marked as favored? So here is how it is calculated. So AFL actually maintains something like a dictionary in Python. So it's basically a set of key value pairs. So what are the keys? The keys are the basic block transitions covered by all the current seeds. So these are the keys. And the value of a key is actually a list of seeds that could cover that particular basic block transition. So then AFL will sort the lists for each key according to this value here, the execution time of that particular seed and the file size of that seed, and from small to large. And the smaller the value is, the more AFL favors that seed. So every first seed of the list are marked as favored here, are marked as favored. So you can see the set of favored seeds are the small and fast executing seeds that can cover all the branches we have encountered, because we use the key, we use all the basic block transitions as the key here. So we need to have one favored seed for each key, right? So all the favored seeds could cover all the branches. It's like a minimal set it's like a minimized set of seeds that can cover all the basic branches that could be covered by all the seeds. So this is how it works. And actually, just now we mentioned that there's a utility tool that can help us to do the minimization of seed corpus, or the set of seeds provided by the user, and it actually essentially does the same thing of selecting the favored ones. So this is how it works. And that's all about how we select the next seed. And remember, in our last lecture, we mentioned that there's a second decision to be made during fuzzing after selecting the seed. After we have selected a seed, we need to determine how many new test inputs should we generate based on that seed. And AFL actually calculates a performance score for every seed. And it is mainly based on the execution and coverage, execution time. Why I say mainly here? Because there are many more design details. And you can have a look at the source code on your own later. So this is a link to the exact line of code. And remember, this single file is like 8,000 lines of code. And this is how AFL calculates. So it basically favors, so it basically favors fast executing seed with large code coverage. So that's the basic idea here. And that's all about the strategies about handling seeds. And now let's learn more about how AFL does the mutations. So there are mainly 4 types of mutation strategies, and some of the concepts might be overlapping because deterministic and non-deterministic could cover the other 2. So the first one is called trim, and the second one is deterministic mutation. The third one is non-deterministic mutation, and the last one is dictionary-based mutation. So for trim, it's actually this mutation operator is not commonly seen in other gray box fuzzers, but it is very useful. And AFL, as we could see just now, AFL favors smaller seeds. There are 2 reasons behind this. The first one is smaller seeds are faster to be processed. So by both AFL and the original target program. So because we are dealing a smaller section of memory, right? Whenever we are dealing with smaller files, so it's faster to process, and it is more compact, which means that because for a program for a file like the PDF file, when we want to mutate the file randomly, not every byte has the equal effect for code coverage, because some of the file content are not determining how this file is parsed. So they are, even if we mutate the file content, the raw data of the PDF file, we won't trigger new program behaviors of the PDF parser. So that's why some bytes, like the structural related bytes in the PDF file, they are more important to be mutated, to be changed during fuzzing. So if we have a smaller file, we are more likely to hit the critical bytes when we do random mutation. So AFL actually tries to trim every seed, and this is how it does the trimming. So it will try to remove the bytes from the input and see and execute the new input with some bytes removed, and see if the coverage is affected or not, is reduced or not. So if the coverage is not affected after removing those bytes from the seed, then those bytes are removed. So this is how AFL trims the seed. It is very useful in practice, because if we can trim down very large seed, we can have faster execution speed. We can have a higher chance of hitting the critical bytes. But for some simple toy programs we write, this behavior may cause some confusion, because for the smaller toy programs we write, we don't have very complex input handling features or input handling code. The AFL may trim down the initial seed we provided to the program to maybe 1 byte, and then it will never generate meaningful inputs with that 1 byte seed. So sometimes when you are playing with some online materials, maybe they have some toy programs, and AFL might be behaving weirdly with those smaller toy programs if you don't disable the trim feature. And the second type of mutation operators is called deterministic mutation. So basically, deterministic means that with these mutation operators, AFL will generate a fixed set of test inputs for a particular seed. Fixed means fixed amount of inputs, test inputs, and fixed content for each one of the test input. So we can get all the mutation operators from the UI here. So the first set of deterministic mutation operators is to flip every bit of the input file one by one. Flipping means turning the value from 0 to 1 or from 1 to 0. So this is deterministic because given a particular input, the way we can flip every bit is always the same, right? So this is why it is called deterministic. And we can also flip two consecutive bits together, and 4 consecutive bits, and so on. And we also have byte level flipping. So like flipping 1, flipping 2, flipping 4 bytes. And there are arithmetic mutation operators, which means plus or minus some predefined numbers with 2 bytes, 4 bytes, and 8 bytes. And it also has some interesting integers to be inserted. It will try to replace. AFL actually maintains a list of interesting integers for short int and long int. So basically, those are the extreme values or zeros or 2 to the power of something for AFL. So it will replace 2 bytes or 4 bytes or 8 bytes with those list of values one by one for the test input. So this is also deterministic. So these are the deterministic mutation operators used by AFL. And AFL also has non-deterministic mutation operators, so which are basically some kind of random mutation. And this is kind of similar to randomsa. So the first type of random mutation is called havoc. So the result of havoc is displayed here. And actually, it's just a random selection of different mutation operators in the previous slide and apply all of them at once. So this is some kind of havoc mutation. And the second one is called splice, and the result of splice is displayed here. So it basically selects, given the current seed, AFL will try to select another seed randomly from the queue and exchange a part of the file content across these two files. So it's like splicing the test input and replace it with the content from another input. So this is splicing. This is also done randomly. So these are the two types of non-deterministic mutation operators. Because they have randomness, we don't know how many test inputs we can get for a particular seed, and we don't know what are the test inputs we can get from a particular seed input. So they are non-deterministic. And the last one here is dictionary-based mutation. So we can use a predefined list of magic bytes to do both deterministic and non-deterministic operations. And deterministic means that because we have a list of tokens or magic bytes, so we can replace every byte or every consecutive bytes in the target input, in the test input, with the token we have. So that is deterministic. And we can also try to inject a token or magic byte after every byte of the test input we have. So that's why it is deterministic. And it could be very, very costly here, because imagine we have 30 tokens, and the test input has 300 bytes. This means that if we want to do the insertion, deterministic insertion, we will do 9,000. We will have 9,000 new test cases, new test inputs. So that's why this could be very costly. So AFL actually limits the number of actually used dictionary tokens by default, but we can tweak that with some options. And here is the link to the default dictionaries provided by AFL. And as we can see, it supports some common file formats like GIF, like JPEG, and of course JSON, JS, PDF, and some other regular expressions or SQL, and so on. So this is an example of the dictionary file. It's just some kind of magic strings for the particular file format. And here are some personal tips for choosing the mutation strategies. And the first one is try to use the dictionary whenever you can. And because for random testing, it's very costly to generate a correct magic string. And if we can have those magic strings in hand, we should make them into dictionaries. And the second one is deterministic mutations may not be as good as non-deterministic mutations most of the times. And because the mutations are too subtle. And when we use it together with dictionary, it will waste us a lot of time executing some test inputs with very small changes to the seed. So it may not give us very good result. And we can use operations. We can use command line options in the fuzzer to disable those deterministic mutation operators. In AFL is -d. In AFL plus fuzz is -z. And the last one is, the last topic here is parallel fuzzing. So we can run, because nowadays computers have multiple cores. And by default, each AFL instance is binded to a particular core of the CPU. So you can see here, this is showing some kind of CPU usage. And actually, each instance of AFL is binded to that CPU. So it will make use, if you use some process monitor like htop, you can see that every core will be occupied by AFL instance to have 100% or even higher usage for that CPU core. And this is done with the source code at this line here. If you're interested in how does AFL do it, you can have a look at this line of code. And for parallel fuzzing, so we are not running them just in parallel without communicating to each other, because in that case we are doing some redundant work. Because let's say one particular instance has made a finding of a new execution path or a new branch coverage, it should be announced or it should inform the other instances, right? And in order to do this, information sharing, they are actually sharing the seeds they have discovered. So each one of the instances we run in parallel is aware of the folder to store the seeds of all the other instances running in this fuzzing task. So normally when we do parallel fuzzing, we will have one master instance which we will have the deterministic mutation operators enabled, and we will have multiple slave instances with deterministic mutation operators disabled. And you can think about why master instances, why only one instance is allowed to do deterministic mutation operators. You can think about it on your own. You can think about it. So I won't discuss in too much of details here. And different instances, since they are aware of the existence of the seeds from other instances, so they will crawl the seeds discovered by the other instances from time to time and put it in its own queue. And this is, as you can see from the UI here, you can see the imported. So this imported here means this slave has crawled 2,000 seeds from other instances of AFL. So this is how it runs in parallel and shares the information. And that's all for the lecture. And we do have a practice session for today's lecture. And here is the practice. The practice is to actually do gray box fuzzing with AFL to see how it works in action. And in order to use AFL, you have to install it. And it's better to use Docker here because of the LVM version issue. So it's better to use some older versions of Linux. And these are some commands to build AFL and install it. And if you are running AFL for the first time, as I just mentioned, you have to set core pattern of the CPU as a root user. So you should get root access using this command. And if you are inside the Docker, you don't need to do this. So basically, you just run the following commands to set the core pattern. The core pattern is to deal with crashing inputs. And this CPU scaling is to actually change the CPU mode to high performance. It's essentially the same as changing the CPU to high performance in Windows. But it is done in command line. So that's what the commands required for running AFL. And let's have a look at how do we fuzz a real world program. And this program we use here we use as example here is called llama.cpp. And this is a repository of llama.cpp. You can see it's like crazy. It's a very new project which was created like just in this year, and it has received 66K stars. And the reason is because it is actually an inference engine for Meta's Llama model and some other large language models. Because large language models are, you may wonder how does it run in background, right? Or not? You're not interested in how large language models run. So they are actually running with some engines, and this engine will incorporate the computational resources of your computer, like your CPUs, like your GPUs, and it will use these computational resources to run the model for you, to run the inference of the model for you. And so that's why this project is so popular. And in order to run the model, it has to accept the model file as the input here, right? Since it accepts an input, we can fuzz it. It accepts a file as input, then we can fuzz it. And the file format used here is called gguf file. So the file extension is gguf. And those are the models, large language models. And in order to run this gguf file, the first step to be done by llama.cpp is to parse the file, the gguf file, and then it can execute the file and do the inference. So basically what you can see is here. So if you have a model.gguf, you can use llama-cli -m followed by the prompt, and it will generate the output for you. So it basically works like this. And because we are not interested in how it does the calculation here, we are only interested in how this how the file is parsed by llama.cpp. So we don't need the following commands here. We just need this command. So remember, in our lecture, in the workflow, what we do first is that we need to instrument the target. And I have already instrumented the target here, but I will do it again, just to demonstrate. So have you used CMake before? Yes, that's good. So this project uses CMake to build. And let's do this. So basically for CMake, we need to make a new directory called build to store the build artifacts of the file of the project. So build maybe not new because I already built it with the build folder. So let's do this. cd inside this. So you need to be familiar with different building systems in order to use AFL. You need to be familiar with these. Not this one. And inside the build folder, what we do is we invoke the CMake command. We invoke the CMake command and replace the compiler with AFL's compiler. So in our slides here, where is it? In our slides here, we have introduced the compilers made by AFL to do this instrumentation. So you can use any one of them. You should use the proper ones, although because GCC is only for C and G++ is only for C++. Or if you have LVM level of instrumentation installed, you can also use these two compilers here. But I don't have it installed on this laptop, so let's just use the default GCC and default AFL G++ to do the compilation here. And here are some flags for C and C++. They are just to use the address sanitizer, which is to, I have been mentioning this term in our lectures before, and this is to make the fuzzer more sensitive to errors inside the program. So, and we will learn more details about sanitizers later. But let's just use it for now. And so we can run CMake to create all the make files. And then we can run make -j to make them. As you can see, during the compilation, we can see AFL is actually instrumenting the target. You can see it instruments many locations automatically during the compilation. So each instrumented location is actually a basic block here. let's wait for a while for AFL to run this instrumentation. You can use htop to monitor the process. And this is one instance I ran without using a dry sanitizer. So as you can see, in 12 minutes, AFL has actually found 250 seeds, including the initial ones I provided to AFL, and it has found 24 crashes. And this is a command to run this fuzzing here. So the command is we need to specify the initial seeds we provide to AFL, and in this case, the initial seeds are GGUF files, and we need to specify an output folder which will be used to store the fuzzing results. And this one is to not limit the maximum amount of memory to be used by the target program. And this one, followed by the two dashes here, is the command to execute the target program. Remember, from the README file of llama.cpp, you can see that our model file should follow the -im option here. So this @@ is a special symbol used by AFL as a placeholder for the actual file in the original command we run the target program. So this is how we run this fuzzing here, and let's see, the compilation has finished. Okay, that's good. So let's get back to the steps here. So the next one is we need to prepare the seeds. So I have already prepared the seeds for you, and you can download them from this link here. And let's just copy the seed files. Here, let's just copy all the seed files here. You can see inside the folder, they are all just some random GGUF files as the initial seed we provide to AFL. And then what we can do is we can start running the fuzzing process. Let's try to skip. Like I just mentioned, it's better to skip the deterministic mutations normally. So let's skip it with the -d option here. And then we can start fuzzing. So this is a dry run stage, which means that AFL will try to go through all the initial seeds we have provided to it, just in case that the program crashes with the initial input we provide. So that's the dry run stage. And you can see AFL will try to do the trimming, and immediately it finds some crashes. It could find some crashes. And let's have a look at the crash it has found. This is not because llama.cpp is not a good project, it's a vulnerable project. It's because it's a new project that has not been fully tested yet. It's still a very, very powerful project, as you can see here. It's a little bit buggy, but it's definitely a good project. So the binary we have built is this one, followed by -i, and the output folder we have the crashes. We can see all the crashes here. So let's run maybe the first one. As you can see, it actually cannot allocate a very large amount of memory here. It fails because of this. So this is not really a valid bug in the program. And just now, the advantage of using address sanitizer is that it can help you to generate the stack trace of the target program when it crashes. But the drawback is that it will always report signal 6. So whatever reason fails this address sanitizer, it will always throw an abort. So this is a drawback here. So all the signals we found are with signal 6. However, if we don't use address sanitizer, we can see that AFL can actually find some non-assertion bugs. And assertion fields in many commercial or many mature projects, it is considered as a valid bug. But for this one, this is a new project. And although it is popular, normally we don't report assertion fields to the developer. But this one is a valid bug. This one is a valid bug. Let's see how it works. So the signal is 08, and remember 08 is a floating point exception. It's an FPE error. Normally it is divided by 0 bug. And we can see the return value should be 136. You may wonder why 136 is signal 8. It's because 136 minus 128 is 8. So if we have a segmentation fault, which is, if I didn't remember it wrongly, it should be 11. So the return value should be 139 for that, for segmentation faults. And we can see this is roughly how AFL works in action. And if we don't stop the fuzzing process, it will run forever. And normally we should do more than one cycle of fuzzing if we want to find bugs in real-world programs. And this is roughly how it works. And as for the practices for Flex Week, because you will be using some Greybox fuzzers, not just AFL for your assignment tool. And the idea is you can practice using some of the fuzzers in Flex Week and try to find bugs in llama.cpp. And if you have found any interesting bug, which is not just the assertion fields of the llama CPP project itself, if you have found any interesting bug, you can tell us, and we can report it to the developer, and you can make some influence to the community. So I don't know if llama.cpp is in bug bounty or not. If it is in bug bounty, you may earn some pocket money here as well. So let's see. And I will add more instructions or more materials of the other fuzzers, Greybox fuzzers you could use for practicing. And let's just try to fuzz this project here. And you can see this is actually a repository. This is actually a bug bounty platform, so it helps to provide bounties to different projects. GitHub repository URL, okay. Okay, let's try to look at here. Llama.cpp is not, unfortunately, is not accepting bug bounties here, but I believe maybe there are some places where it accepts where it has bounties. And you can see that there are many projects here which are written in C and C++ that does have bounties, and you can try to fuzz them as well to see if you can really earn some money with by finding some interesting bugs. So actually almost all of them are related to machine learning and deep learning now, the bounties. And that's pretty much of it. I will add more materials for the practices for you to try out during Flex Week, and I will inform you on WebCMS. And once you have returned from Flex Week, you will receive your assignment 2 specifications in week 7. And that's all. Hope today we have a lot of content, and hope it's not very overwhelming to you. And if you got overwhelmed, I can see from some of your face. And if you feel this is kind of overwhelming, you can always ask questions on the forum. Okay, that's all for today. Thank you.